Testing, testing. Testing, testing.
let's make sure it's on.
So sorry. Are we starting or how?
We're going to start.
Okay, yeah, all right.
All right, everyone. We have saved the best for last because I see the announcements for another version of Asymptote come out on C10 on a regular basis. Mm-hmm. And every once in a while I ask, well, I better go see what's changed. Mm-hmm. And I suspect we'll learn more about what has changed. So let's welcome John Bowman from University of Alberta. Past, present, and most importantly, the future.
Thank you. Can you all hear me at the back? I've got a lot of things to hold, and I'm not sure I want to hold a microphone too. So, okay. First, I want to acknowledge my collaborators. Andy Hammerlindell was the one of my undergraduate students back in 2002, and he came to me looking for a summer job, and this is what came out of it. It was Asymptote. So here we are. About 25 years later, and another collaborator here is Charles Staats, who's with us here today, and he's contributed a lot of what I have to say in this talk. And also the software that was used to develop this talk was developed with my student Ben Bingham and also with AI. AI is what pushed it over in this last week to get, for the first time, some of the features I'm going to show you available in a PDF. So, right, so the talk is posted here, and there's a QR code. If you're close enough with the camera, you can take a picture of it. Anyway, so it began in 1978, but I guess the manual came out in 79 for TeX and Metafont. So in the beginning, it all started with Knuth. And then at that point, the companion to TeX, of course, was the font generating program. That was all done with bitmaps. And so now, we're using much nicer looking fonts, and that's due to the work of Hobby. He realized that the problem was really figuring out how to pick control points for drawing nice, smooth looking curves through some points that you specify that you want to use for making your fonts. And so he developed this concept of mock curvature. It was efficient. It could be solved with just a tri-diagonal solver. And that was very important back then, so that you could very quickly calculate these control points, and then they can be rendered by subdivision very efficiently. So, so that was for producing fonts at that point. But then in 1989, Hobby realized that he could, if you can make nice fonts, then well, you could also make nice curves and do graphics. And so that was what began Metapost, and Metapost is what inspired Asymptote. Because when Andy Hammerlindell came to me and looked for the summer job, I said, well, there is one thing I see. There's this program Metapost. I've been trying to. It seems to be the best thing out there for this Venn diagram I wanted to produce, and I wanted vector graphics. That was one requirement, but I also wanted IEEE numerics. And of course, this software was all written before the IEEE standard. Back in 1978, it was before the IEEE standard was a thing, and so I wanted to modernize Metapost, and I looked at the code and I thought there doesn't look like any way we could upgrade the numerics. It's too based on TeX. So my decision was to go away from TeX, use TeX, but redo the whole numerics. And Andy, I gave it to Andy and asked him, well, take a look. Maybe your opinion is different. But he came back a few days later and said, yeah, you're right. We're going to have to start from scratch. And so 6 months later, he read a book on compilers and wrote his own compiler for a virtual machine that could produce a little straight line. And I thought, well, that's pretty cool. But how about let's make a sine curve or something? Well, he said, well, we can't do it yet because it doesn't know about sine, but let me type on your computer for a minute, and hack, and he hooked it up to the floating point sine instruction, and lo and behold, we had a tiny little sine wave, and that was the beginning of Asymptote. And then I was at a conference, and I learned how to overlay with TeX because this was just producing PostScript at this point. There was no tech involved at all. But, and unlike the way it was done previously in MetaPost, I diverged from the method that was used there. I wanted to really use tech itself. And I didn't want to get into redo what Knuth did, because he did an excellent job with typesetting. And so let's not reinvent the wheel, let's build on that. And so Asymptote at that point was just a way of producing a tech file for you that would bring in with include graphics, or whatever we used back then, EPSF or something. It would bring in your graphics and interlace it with tech. And, but that was all 2D. Then in 2005, so this was our first public release. We started in 2002, but it wasn't released until then. And it's the same time that TIX was released, and neither of us knew about each other's projects. Otherwise maybe there could have been some collaboration there, but we did really choose very different approaches to the problem. The fact that we didn't really build into the tech ecosystem, we just used it. Okay, that gave us freedom to do more things, particularly when it came to doing 3D. So the trouble with 3D is, first of all, tech is a 2D program, and at the last TUG meeting I was at back in 2010, I met John Hobby and showed him what I was able to do and the difficulties I had extending his algorithm, the same mock curvature algorithm, but a generalization of it into 3D. And there are some issues, some parity issues that you have to deal with. And that's all in this publication here. So that then gave us the ability to lift tech into 3D. And we wrote an OpenGL renderer and even figured out, I had a student, Urs Shard, who helped me figure out how to embed this in PDF using this legacy PRC format. And if I was giving this talk back then, that's what I would be using to show you 3D graphics. Unfortunately, PRC, I'm going to discuss, is not a viable option anymore, and we need something else. And that's partly what this talk is about. So another thing that happened shortly after that was because the labels in tech, even though I've lifted them to 3D, they're still planar. And if you rotate your graph, you'll be viewing those labels edgewise, and it's not going to look very nice. So one of the important advances was allowing those billboard labels to rotate so that they always face the camera, no matter how, and you'll see examples of that, no matter what viewpoint you're looking at. And there were various 3D PDF enhancements which were done with a colleague from Russia, Mikhail Vidivosov, and that's mentioned in this article, in another Tugboat article. And another missing feature at that point that we added in with Bezier triangle patches. Those are useful. Bezier triangle is a natural generalization of a triangle to 3D. Then a student who goes by the name of Jamie, Rasame Masmuang, and he independently contributed a better rendering model than the Phong blend model, which I was using. I was just using the simplest model. He uses this PBR-based approach, a more physics-based approach, and also image-based lighting. I'll show you an example of that. And he helped me develop this WebGL output format using a JavaScript library that we wrote together. And Jamie also helped me develop a replacement to the PRC format that I mentioned. It's a new format. I call it Vector 3D, V3D. And it's compressed. It's even better compression than the PRC format. That was one of the big deals about PRC. The trouble with PRC is one of the way they implemented their own compression algorithm. There's good compression algorithms out there. I didn't have to reinvent the wheel. So we used gzip. And also another thing that's been missing from 3D graphics up to this point, so 5 years ago I finally implemented exact pixel perfect order independent transparency in 3D. And that's really hard to achieve and to do it efficiently. And the problem with transparency is what makes it so hard mathematically is that the blending operation that we use is non-associative. And it means you have to sort the fragments that get mapped to a pixel, you have to sort them usually from back to front, and you can't interchange that order. So although with opaque objects, the painter's algorithm allows you to graph in OpenGL in an order-independent manner, that all breaks down when you have transparency. And to do this correctly, you need advanced hardware features of the GPUs. We all have those features, but the software is kind of lagging, and that's one of the problems, as we'll see. There have been a lot of language improvements thanks to the work of Charles Staats. He introduced the templated imports, the using and auto-unravel keywords. I'll talk about those briefly. There's a front end, XASI, a graphical front end that's been upgraded recently to use Qt6. And this collections library, also introduced by Charles Staats. He put a lot of work into this. It's a massive project. There's an iteration facility with an iterator operator. You can now index, have user-defined index operators on your structures. So you've got hashing. And the most recent thing we've done is a big thing that I'm sure that Carl is looking forward to helping me with next year in the Tech Live release. We have transitioned over to Vulkan, okay, and all the wonderful Vulkan libraries. We'll have to be talking about that next year, yeah. I deliberately saved this Vulkan transition until after the 26th release. Yeah, I knew you would be happy. And then what I'm using for this talk is this V3D Aware PDF plugin, which we just got to get working this week. Okay, so it's very brand new. Okay, so for this, it's used for this talk. Okay, so this is the one of the important contributions. Sometimes you want to import a module in Asymptote. You want to write a generic module for different cases, different types, and you don't have to have different copies of that module and have to maintain different copies, one for each type. You know, maybe one for reals, one for ints, one for complex numbers, or whatever. Or maybe it's a sorting algorithm or something. Whatever. We wanted a way. We had some kludgy ways of doing this before. Now we have an elegant, robust way that involves in your module, you tell it that there's a generic type T and a generic type S and another one called number. And you can now, when you actually go to import this module in the calling module, in the parent file, you can access it using telling it what T is and what S is in this particular instance. And Charles recommends you can call this module anything you want. You have to say as something. But he recommends, it's a good practice, that you actually name the module with some indication what these different types are, because you may have more than one access of a module with different types. Okay, so this enables generic type-safe library code written entirely in Asymptote. And we also, just like C++, we added a using keyword instead of a type def. And it's just more convenient. It's not so backwards like type def is. And to many of us, we always felt it was the type def is a little bit awkward, and it actually is necessary in this language when you're referring to function types. In certain contexts, you need to use this type def. It's actually required. It's not just a convenience. This makes it a little easier. And there's also a new auto-unravel feature, which is quite convenient. What that does is if you have say a structure with a member function, an operator plus, that operates on two of those structures, rational, for example. So this is an example of a structure that implements rational numbers, and you want to add two rational numbers. If we didn't have this auto-unravel keyword, this would have to be declared outside of the structure. And this way you can keep everything nice and self-contained, and you can still access it outside. The auto-unravel basically unravels this out of the structure so that the plus operator is now accessible wherever rational is used. And so that's really nice. And then Charles went on to develop all kinds of containers to help us out with some functionality that we were missing, or it was very awkward to do these things before. And so this is a very, very thorough packages set up for doing hash maps and hash sets, sorted sets, queues, and also native hashing of ints, strings, reals, and int arrays. They can be used as map keys. For example, so from his collections library, you can access, it sort of looks a bit like Python, right? I mean, the from part, right? And you're accessing this module is this key value hash map. You can access it as this particular name. Again, I'm following Charles's recommendation. And then that's now a type that you can use. And so we're going to, the instance of that type we're going to use is little h. And then we can now, it's like a dictionary. We can assign to various strings, we can assign some integers, 4 and 2, and then we can write them out and we get 42. Okay, so another example, you might be doing a frequency analysis on pets, see which are the most common pets. So you got a list of pets. And I didn't have room here for a long name, so I just called my hash map h. So I create an instance of that hash map called counts, and I can iterate on it, and so I simply increment for each. I go through this list for every pet. I do a frequency analysis, and so I know how many pets I have of each type, and then we can graph it out. So this is just the code for producing this graph, and you see that the cats win. There's 3 cats and 2 dogs and 1 bird. Okay, so another thing. There are some iterator utilities, zip and enumerate. Here's an example of how you use zip. It just allows you to, like a zipper, go back, join A with 1 and B with 2 and C with 3. And so we write them out here. So basically, it's another way of doing key value pairs. But you can combine any 2 arrays this way. You can zip them together of the same type or different types. So also these bracket operators, if you suppose you define your own structure, you might want to define what the bracket operator does on that structure. So that's quite convenient. We couldn't do things like this before. And so these are all enhancements to the language. Okay. Now I want to talk about what's been done on the rendering side. So all the 3D work is based on Bezier surfaces and curves as well. But the most difficult part are the surfaces, because you have to deal with occlusion and lighting and subdivision cracks, rendering, all kinds of issues. The fundamental atoms of 3D graphics for Asymptote are Bezier triangles and patches. So Bezier triangles are the natural generalization of Bezier curves to surfaces, just as triangles are the natural generalization of straight lines to planar surfaces. So the Bezier triangles are curved, and they also have a one interior control point that you can use to lift the interior up or down a little bit. So they have a total of 10 control points. A Bezier triangle can be conveniently expressed in barycentric coordinates. By the way, I'm talking about the cubic case here. Okay, this is the usual case that's used in computer graphics. We're using cubic splines. Okay, so Bezier patches, they're the direct product of 2 such Bezier splines, okay, 2 Bezier curves. It's the direct product. And they're like the generalization of quadrilaterals to non-planar surfaces. Okay, so you've got something like curved triangles and curved quadrilaterals. We call those Bezier triangles and Bezier patches. Here's a Bezier triangle, and this is now done with the new plugin that allows us to have finally, back in 2010, even 2008, I could do this when I was teaching, and I could, when I had surfaces of revolution in my calculus classes, my students were on their laptops, and they all had Adobe Reader, and they could view this with Adobe Reader. But unfortunately, Adobe Reader a few years later was no longer supported on the machines, on the new machines the students had. They had tablets and phones, and also Adobe Reader stopped supporting Linux and other OSs. So they still, I guess, support Windows and Mac OS, but very few people seem to use them. More people are using things like Chrome browser and other browsers out there. So it's great after all these years to finally have this functionality that in a PDF presentation, that I can do graphics without having to leave the presentation to another piece of software. So, so let me just mention a few of the problems of this PRC. It stood for Product Representation Compact. It was a French product. They also had the acronym PRECISE because it was meant to be very compact and precise. And, but the problem is it was only, no one wrote a reader for it. We wrote a writer, and we could have turned all the write statements and read statements and made a reader for it. But there's other problems too, okay? Also, another big problem is Adobe Acrobat, even though it sort of worked, it wasn't adaptive. It was not vector graphics. The initial mesh you got on loading was the mesh you got when you zoomed. It never got better. So that's not vector graphics. So, and it had no 3D transparency. It didn't have vertex-dependent colors, which made everything look really, really pixelated when you did scientific graphs. And no Bezier triangle support. So I used AI to help me prepare this talk, and the AI wanted an example of PRC. It says, I can't put an example in. That's the whole problem. That's the whole point of the talk. I can't do it anymore. So we developed a new format called V3D and Vector 3D. It replaces this legacy format. It's a portable compressed vector graphics format for 3D scenes. It's embeddable in PDFs. And it's importable back into Asymptote. And it has 3D transparency. It has all the things I want, vertex-dependent colors. I basically put everything in that I want. And we're on version 2 right now. It's an integer. We're going to just keep incrementing the integer as people submit new, request new features. We can always extend it. It has also some primitives built in, which are common primitives in graphics that you can use in drawing. For example, tubes are very useful if you want to draw a thick line. In OpenGL, you can only be sure of a 1 pixel wide line be supported. That's all that the standard guarantees. So if you want to draw anything more, you have to draw a surface around that 1 pixel line. Also, we support triangular groups, which are useful for tessellation. And also curves in 3D and even pixels. As I said, there's a bunch of viewers for these for V3D. We're working on getting more available, but one of them is Asymptote itself. It can read its own files, which is always nice. And there is a library for programmatic access to it. But the real tools that the real tool that we're going to encourage people to use for the time being right now is Ocular. We've developed a plugin for it, and that's what I'm using today. And so I will announce it soon once it's completely stable. If it survives this talk, that's already a good sign. It hasn't crashed yet. There's also, we've had for some time now, for a year or two, we've had this online JavaScript PDF viewer that can read V3D. And so that's another possibility. You've got to read that through a browser. So here's an example of, I think I showed this in 2010, this whoops, I forgot, I can't zoom that way. Okay, when you zoom, you're scrolling the document. When you use the mouse wheel, it scrolls the document. So I don't want to have contention between two. Normally the mouse wheel would zoom like that. But anyway, you can see that I've really lifted tech into 3D. And Donald Knuth really was impressed with this when I showed it to him, that to see his work now in 3D. And it was a lot of fun doing this. And this is just a little, there used to be this package, PS Tricks. Anybody ever use it? Anyway, you don't need it anymore. There's better ways. Okay? Okay, and here you see the billboard labels. Okay, and maybe I can zoom in a little bit so you can just see them as they rotate. As we rotate around, they don't disappear. They're always facing the camera. And the other thing that's nice about this picture is that you don't see pixelization. Oh, sorry, I forget. I can't zoom like that. You don't see pixelization. If I showed this with Adobe Acrobat, you would see all these. You'd basically see the mesh, and that's not good. So underlying this, there is a mesh that I used to generate that. That's a 3D gamma function on the complex plane, by the way, and so along this red, you're mapping a function from R2 to R2. It's a 3D graph. The fourth dimension is I use the color wheel. So red means real, And RGB goes around that gives you the phase of the complex number. And I'm plotting the magnitude here versus the real and imaginary parts. And the factorial is just along here. So you can see how this is very good, useful for teaching to be able to do this. So that's the factorial right up there, the usual factorial along the real axes. Okay, so this is just showing you that we've implemented transparency. Whoops, and we just got this working this week, and AI did this for us. It was like a 3-hour session with my student, and this is all local AI. I'll tell you about that more. Here's another case where transparency is useful. There's a graph here, and you see there's some data that's above the plane and some's below. You still want to see the data, but you might want to be able to understand what's in front and what's behind the plane, or above and below. Here's a nice calculus problem. So there's an exercise afterwards. You can calculate the surface area of the sphere that's inside the cylinder, and that's a fun exercise. And again, we have transparency in that example. This is the Riemann surface, the Riemann sphere, and which shows you the projection of the sphere onto the plane. It's a very nice way of understanding the complex world that we live in. And Charles contributed this wonderful package for drawing smooth surfaces. It's just beautiful. Yeah. So it's interesting how he did that. And he used Bezier triangles. Once we had them available, he updated his tessellation of this so that it makes use of both quads and triangles, Bezier patches and triangles. Okay, so like I said, we've migrated from OpenGL to Vulkan, and but we didn't force people to you don't have to use Vulkan. If you don't have the library available, there's a fallback to OpenGL. Okay, so we dynamically load the OpenGL library. But eventually, I think, especially for Mac OS users, they definitely want to install the Vulkan library, because otherwise, they don't have transparency. And that's because Mac OS basically deprecated OpenGL. Their OpenGL goes back to 2013, and they just froze it there. And so all the new features that we need, the new feature we need is from 2013, and it's not in there, and to have transparency. So that is now available through the Vulkan using Molten on top of the Apple Metal platform. This gives consistent rendering across all operating systems, better GPU utilization. And finally, I mentioned that we also produce WebGL figures. So this is a way of embedding 3D figures directly in HTML. And it's using a JavaScript library that you either download from the network, or you can embed it in a standalone file if you want offline access. And in this way, this brought Asymptote, not the program, but the output, to tablets and phones, but with a little bit of a drawback, is there's no order-independent transparency. So we have to solve this problem. And in order to do that, we're going to have to migrate to WebGPU. But here's a nice example that I just did recently. I added the ability to do animations by specifying, before you draw a surface, you can enclose it in a transform, begin transform and end transform. And this is a function that's going to map your coordinates and time to another function, to a new coordinate. So this is giving some affine transformation here that we're doing. And here we're going to, that's the geometry transformation. There's also a color transformation. So you can change depending on the position and the color and the time, you can do something fancy, and it leads to something like this. So let's click on that and see what happens. Oh my. It's just craziness, right? I just had lots of fun. Deconstructing the Utah teapot. Okay. All right, so that's that example. And here's another example. It was contributed by an Asymptote user who also contributed to the animation. He certainly, by asking good questions and even submitting patches, he helped make this possible. So, this is a robot. So he's I guess he's a robotics engineer. And I don't know his real name, but his handle is Asm Warrior. And you got this robot. You can move it up, and so you can even let's see. You can do that, and what do I want to do here? Then okay, and then move it up, and we can try to reach out and grab you or something. Okay, so all right. So that's fun for educational purpose for sure. And as I mentioned, we need to improve on WebGL by upgrading to WebGPU. So that's a project in the next months. I'll be working on that, and that will give us access to the hardware features like shader storage buffers and that are on GPUs, the SSBOs that we need, and this will also improve the performance too on modern GPUs, and it'll give us order-independent transparency. That's the main thing. And another thing that that my former student Jamie did was this image-based lighting, and I'll just show you an example here. Isn't that cool? And it's all interactive too. You can move around here. There we are. Yeah, isn't that cool? I look at that figure, and to me it looks like Edmonton in the winter. Okay, so you got the snow and you got the evergreen trees. I think it was actually from Russia, but it's pretty much the same thing. It's not the end of the world, Edmonton, but you can see it from there. Yeah. Okay, so yeah, as I mentioned, we also did an upgrade of Qt of Xazi to Qt6. That was necessary for compatibility with different distributions, and Xazi allows interactive editing of asymptote figures. You can modify existing objects, you can draw new objects, and you can save those objects either as normal asymptote files or in another format that allows you to go and edit the objects that you created. So it kind of combines the best features of script-driven and graphical-based methods of figure creation. So it kind of marries these two approaches. And so just in summary of what I've told you today, there's some new language features, template imports, the most important one, and the collections library, these new the bracket indexing and things like that. Sometimes these are syntactic sugar for things we could have done before, but they're nicer looking. And then we've got the Vulkan port, the WebGL, image-based lighting, triangle patches, lots of things, a huge long list. I was surprised when I saw just how much that we've done in the last, since I last spoke at TUG back in 2010. And yeah, and then this plugin we've used. And so in the future, well, I don't have a long list here of things to do, but I'm sure that I can't predict the future, but I'm sure there will be many things. But I've already mentioned the WebGPU migration. That's really important. And we would like to add animations, just like we have that animation. That was only on HTML. I'd like to have it in V3D, so I'm going to have to modify my V3D format to support animations, maybe doing something similar. And here's the last one I've learned at this conference, the need to support accessibility. Now, how to do that in graphics is a real challenge, but I'm certainly interested in hearing ideas about it. There was a project to try to add Braille support for Asymptote, and I should inquire what the status of that is. Okay. But thanks so much for listening, and then I hope that I'll have a chance to talk to you all at the banquet. Yeah.
Thank you.
Oh, here, by the way, is this is our logo, and also on this page, this is the controller that I wrote for doing local AI. I run this talk was partially written by AI on a 5090 NVIDIA 5090 card, and using the Qwen 3.6 model, which is really an awesome model, as Matthew was saying the other day. So you can get this controller from there. It does agentic AI operations in a sandbox on your local computer, and it works much better than using ChatGPT or Gemini or something. So you may want to try it out. Yeah.
Okay, now surely there's a question. I'm looking at you, Boris.
Boris always has a question. You can help us out, right?
I
Only comment, right?
Yeah, I have a comment
Of course.
from chat, and it's very short. It just says bravo.
Oh, oh, you're welcome. I think we have a question here.
So for the generic functions you added, there's no type inference there. You have to manually name the function for each type.
So the generic functions, are you talking about the using keyword we're
Yeah,
talking about?
yeah, because you just specify this different name for every type, so it can't just use type inference to figure out what you mean.
That's right. Yeah,
Okay, yeah.
yeah. Oh, okay, well, maybe Charles can answer that. Yeah.
The functions can be automatically inferred. The types, based on what parameters you cast. Okay, yeah.
Yes, that's true.
The function you can have one name for the function, and there's no worry about name collision. But the type you have to. That's magnetic. You have to have a different type. Well, if you want to avoid name collisions, then you want to rename the type every time you import it with a different set of parameters. In a lot of languages like C++, they use angle brackets for that. I didn't want to try to add the new angle bracket syntax, so we use underscores incorporated into the type name. And if you really don't like underscores, then you can make up your own convention and incorporate that into the type name.
Okay, thank you.
Yeah.
I'm sure I don't need the microphone. I can project my
Well, for our online people, we need it. Yeah.
Hello, this is Jasper. My question is related to a module of Asymptote that I am aware of called Smooth Contour 3, which lets you plot implicit surfaces.
Yes.
I've seen that used to perform things that are very similar, in my view, to partitioning. I have a picture on my laptop here. I'll probably show it to you afterwards.
Sounds good.
I was wondering if that same procedure with the implicit surfaces, such as the genus 3 surface,
Yes.
could be used to handle more advanced partitioning features as they do in, for example, when you have a plane partitioned by a cube.
Yeah, well, one thing, if you have a plane partitioned by a cube, I think the best way to do that is at the pixel level. And we actually have another thing I forgot to mention, which should be on the future slide, is an unfill operation, which is a project that's partially completed. And using AI, I can probably, again, push this one to across the finish line. So in 2D, PostScript does unfill by whenever you draw a pixel, it checks to see whether it's inside a particular Bezier curve or not. We can do the same kind of thing in 3D. We have something, a prototype implemented, but it still has a lot of problems. But that would be how I would try to do that particular problem. But there are more general issues with intersecting surfaces. And so maybe Charles can speak to this, because he wrote this wonderful package. And I know he has ideas on how to do cropping.
I'm quoting
in 3D.
Charles, actually.
Yeah.
I'm quoting his Stack Exchange answer to my post
Oh,
from
of course,
a
yeah.
while ago,
Yeah.
probably from 2025 January.
Yeah. So I don't know if Charles wants to comment more. Yeah, I think he would like to. Yeah. Charles didn't want to give a talk, so I told him, I'll talk about all your work, and then when I say something wrong, you can correct me. And see, it's working. Yeah.
Okay, so I do. It's been on my to-do list for a long time to see if I can use these same sorts of techniques as an alternative to John's approach with the unfill, to see if we can truncate surfaces that aren't defined implicitly. I sort of put that on the back burner because I was really frustrated about trying to do this sort of thing without a collections library. So that's one of the reasons I went to the effort of creating a collections library, is to make it easier to work on those sorts of things.
Well, we have something to look forward to, so that should also be on my future slide. Yeah. Okay. Yeah.
Did you also, when you used OpenGL, did you also use custom shader programs?
Yes. Yes, and I should say that was another thing that should have been on that list that my former student Jamie did. They're still working with me part-time. but they're the ones who got me to move away from begin GL and end GL or whatever, the old way of doing OpenGL to using the shaders. And so because we have the shaders, now we can do wonderful things like the transparency. Everything that's done at the pixel level, we can do it, the unfill operation. It opens up whole new approaches. So we've had that for a few years now, maybe back 4 or 5 years, yeah, something like that. Yeah.
And was it like a rasterizer implementation or deferred rendering?
Deferred rendering. Well, that means something else, I think, in Asymptote, what we call deferred rendering. We are rasterizing, but we're doing it adaptively. So first, what we do is we turn Bezier patches into triangles. We wrote our own. When I say we wrote our in-house renderer, it's just for turning the patches into triangles. Once we have the triangles, we give that to OpenGL and let that handle, because it handles triangles well, using the OpenGL shaders. And those same shaders, with some modifications, worked in Vulkan too, and they're also being used in this talk here. Those same shaders are copied over to the plugin as well. Yes.
Okay, thank you.
Yeah.
All right. We'll thank our speaker one last time. And now, Eric will continue the program.